So, like I mentioned, learning sparse reward tasks, complex tasks like such as multi-agent coordination tasks can be quite difficult and complex to learn using vanilla reinforcement learning approaches. So, this paper, shows task creation for curriculum learning, was the first paper to propose automated curriculum generation approach for reinforcement learning.
Automated as opposed to what?
Automated as opposed to a heuristic based approach, which is maybe semi-automated and specific to a given agent in a given task for a given environment. These can also be these approaches are more so what happens in these heuristic approaches, we don't have any guarantees that the tasks we're generating are learnable by the policies. We aren't taking the
intermediate tasks?
Yes, we don't actually take into account the policy's performance while designing this curriculum. We just design this as a...
but isn't the policy dependent on the task that you're trying to solve?
Yes, but when I need to make the sequence of tasks in my curriculum. So how do I make the sequence of tasks while ensuring that they can be learned by the policy? As I progress along each task in the curriculum, how do I ensure that the next task is something that the policy trained on the previous task can learn?
Okay, so we don't have to pre-commit to the sequence of tasks, to the sequence of simpler MDPs that we solve towards the target MDP, the target task. We can actually choose a simple one, solve it, get a policy, and then decide on the next task.
Yes.
And so on, use the previous policy to decide on the next task.
Exactly. And that's actually what this the key insight in this paper was, that each the curricula that is generated needs to be tailored to the policy. And that really improves the policy's ability to learn to perform
the previous policy. Right?
Yes.
In the previous task.
Exactly. So it sees the policy's current performance based on its performance with respect to the target task, its performance on the previous tasks it's already learned, and using that it generates the next task which would be the most appropriate for it.
Okay, I'll just quickly define a task. I'm not sure if we did that. Right, so a task is an MDP. It's a full MDP that we're trying to solve, or that we apply RL to, reinforcement learning to. But it's not necessarily our target MDP, what we're actually trying to solve, which is very difficult. So what we do, we break it down into simpler problems that the experience that we learn along the way while solving these increasingly complex sub-problems or intermediate problems, that experience will lead us to more efficiently solve our target problem. Okay, and so this is what you call a task, right?
Yes.
But there is some distinction between a task and an MDP?
No, a task is an MDP in a sense.
In a sense, right? Yes. But maybe
you could have, we'll discuss some approaches where task may have similar MDPs but different objectives, loss functions.
So it's some sub portion of the MDP. But for the sake of our discussion today, let's just assume the task and an MDP are similar things.
Yes.
So you're saying one intermediate task, you mean an MDP that is defined for the intermediate problem. Okay.
So, although this approach did a great job in personalizing a curriculum to a policy and help it improve learning efficiency in multi-agent RL environments like Pac-Man, what are the guarantees that the generated curriculum is still optimal? Navreka et al. In 2017 moved on to provide an approach which is also optimal, which does learn an optimal curriculum for a policy by formulating the curriculum creation as a Markov decision process. So now we are iteratively trying to refine the curriculum that we are designing for a policy by continuously breaking complex tasks into simpler tasks that the policy can perform. However, The drawback of this approach is that this recursive decomposition often is very computationally expensive and intensive, so it's not very practical to use in the real world. Several other automated curriculum learning strategies have developed since then. Approaches can be widely divided between task generation approaches, task sequencing approaches, domain randomization, goal-based learning. So starting with task generation methods.
So automated curriculum, you say here automated curriculum, always the automation is for the generating the sub-problems?
Not always. It can
So
be
what
with
is the
task
automated-
generation, but we also have task sequencing methods where based on the available tasks available, they automate what would, based on the policy's performance, they automate and decide what would be the best sequence of these
Okay, so
policies,
sometimes
tasks to train on. Yes.
and in these cases you have all of the tasks or the intermediate MDPs predefined, and you just have
Yes.
to set the correct sequence that will learn or produce effective learning.
Yes.
Okay, and in other cases you actually have to create or
Yes.
define these MDPs.
Yes.
And is there a difference in the name? So both of these are automated curriculum learning?
So
Is there a distinction?
these are known as task generation methods, whereas we'll see also task sequencing methods.
Okay.
Yes. So
Okay, and that's how we distinguish between these. Okay.
So in task generation methods, we have usually two architectures. It can be either a student-teacher architecture or self-play approach. So in a student-teacher architecture, the teacher monitors the student's current progress and appropriately designs a task which would progressively help the agent learn its target goal. In self-play methods,
Well, one second. What is a teacher? So a teacher creates the problems,
yes.
and what is the
It
student?
creates the task. The teacher
Teacher
creates
creates
the
a task.
modifies the MDP for a task
Uh-huh.
to make it simple enough and such that the agent can perform it, but also challenging
So it learns.
enough so that it progresses in learning towards a target task.
Okay, so the student is just the reinforcement learning agent.
Yes.
Okay.
And the teacher is also often a reinforcement learning agent. They both can be trained using their own rewards, but the teacher's objective is mostly to maximize the student's reward. And self-play mechanisms, both the networks being used are random policies, and self-play methods are inherently competitive in nature, where, for example, a policy could compete in a zero-sum game against another policy. They both could start off as randomly initialized policies and compete against each other, trying to improve their strategy and trying to make each other better. And we'll see an example of this soon.
But this is only for adversarial setting or also for single agent setting?
So this can also work in a single agent setting, but the competitive nature of it remains, where even in a single agent setting, the policy trains against its own past policies and tries to ensure that it's always performing better than all its past policies while progressing towards the target goal. So it's always either training against some other comparative policy, which could be its own previous policy or another policy that we're trying to train. Which, for example, we'll see an example of hide and seek soon. So this paper, Teacher Algorithms for Curriculum Learning of Deep Reinforcement Learning in Continuously Parameterized Environments. This is an example of a teacher-student architecture, where we develop a teacher algorithm to guide RL agents in acquiring skills through adaptive learning curricula across diverse environments. So here, like I mentioned, the curricula is designed so that each task is something that the student can learn, and it's also progressing and trying to maximize the learning progress of the student. And they have modeled this maximizing approach using a continuous banded task as a continuous banded task. And they also use a Gaussian mixer module to model learning process, and this can help. They show how this helps guide the generation of the curriculum and how we sample environments for the student agent. Similar to before, this results in a personalized curriculum for the student tailored by the teacher. In their example, they use the bipedal walker domain, and they changed some attributes of the environment of the walker. For example, it's the size of its legs. It initially trains it to learn using smaller legs, and then learn to control larger feet, which could be more complex.